External diffusion is the rate process that involves movement of reactants from the bulk fluid to the catalyst external surface. There is therefore a different concentration of the fluid in the bulk compared to the fluid or the concentration there at the catalyst surface where the reaction actually takes place. It is important to note that we still use the bulk fluid concentration in our mole balance when we calculate molar flow rates, and therefore it is the bulk fluid concentration that is used to calculate the normal conversion like we've done previously. The rate at which this process takes place is governed by two processes or two constants, the rate constant and then of course the driving force for this reaction, which is the difference in concentration between the bulk fluid and that at the surface. This rate constant, and here I've expressed the rate, so you must be familiar with all the rate conversions as a volumetric rate based on the reactor volume. So we have our Kc, this is our external mass transfer rate constant. AC is the conversion factor to make it a volumetric rate, and then our driving force. Kc, our external diffusion rate constant, depends on the properties of the fluid, the diffusivity, that we have got different correlations that we can calculate that, and this thickness of my boundary layer, that little thickness over there, the boundary layer thickness. So which factors affect how fast or the extent of that rate constant? How can we make it bigger so that we've got a faster rate of external diffusion? First of all, there's the fluid properties, and that depends on the temperature, the viscosity, the mixture. The main thing that will affect that parameter in our reactor is the temperature. Please note that it's only mildly affected by an increase in temperature. There's a slow linear increase with temperature, and that is very crucial for you to understand for later parts of this theme. The thickness of the boundary layer, of course, is also a function of the viscosity, but we can affect that by increasing the shear in our reactor to make that boundary layer thinner. In a CSTR, we would stir more vigorously, increase the RPMs, we can change the shape of our stirrer, we can put in baffles in our reactor. In a PF or PBR, we can influence it by changing the linear velocity. And how do we change the linear velocity? We have a smaller, longer tube. So we've got the same mass of catalyst, but the reactants flow faster. So we can influence that by changing the tube diameter in our reactor. There are many correlations for calculating this external mass transfer coefficient, or Kc. Shown here is the Teunis-Kramer correlation that is often used in packed bed reactors. Please note, packed bed reactors not applicable to CSTRs. I don't need you to understand the derivation or even use the detailed version. What is important to me is that you understand the proportionalities in this equation. So you can see that Kc is a function of fluid properties affected by temperature and mixture composition, and stuff that you can control by designing your reactor. So the linear velocity, you can change that by changing, of course, the volumetric flow rate, but mainly the reactor tube diameter. This is the catalyst particle diameter. You can see the proportionality there. So what I would expect you to be able to do in TATS and in tests is to use proration in order to calculate Kc at two different conditions. So if you know Kc at a certain tube diameter, you must be able to use this proportionality to calculate Kc when I, for instance, halve the tube diameter, just like what you've done with the ergon constant in your semester test and in your TATS. For a CSTR, Kc is proportional to the RPMs in that reactor. That depends on the shape of the impeller and the shape of baffles in that reactor, and also, of course, it depends on the particle diameter. So in many TATS, I will actually expect you to be able to calculate these proportionality constants, or they will be given so that you can use them to prorate for Kc at different conditions. So the implication of this external mass transfer, this extra rate step, is that we have an extra unknown in our mole balance, and that is that surface concentration. It's important to remember that that is actually the concentration that you must use when you calculate the rate at which the catalyst can convert A to products. So picture as an example that you are in a restaurant, you are the catalytically active site, and your job is to convert chips into energy and some waste products. So it doesn't matter how fast you can eat if you don't have any chips in your plate. So the rate will actually be dependent on how fast the waiter or the waitress can deliver some chips to your plate. So if the waitress brings one chip in every minute, chances are good that you will have no control over the rate at which the chip is converted, because you will eat it as soon as it lands on your plate, and the surface concentration will actually be zero. The rate controlling step will be the rate at which the waitress or the external mass transfer process takes place. Now, under steady state conditions, what we must understand, under steady state, we can write two mole balances. We can say that the rate at which stuff disappears from the bulk fluid is either equal to the rate at which the chips can be eaten, or the rate of conversion of my product as it happens on the catalyst surface. That rate constant we use there, I use an I to denote that this is the intrinsic rate constant. Also, I can write a second mole balance that says the rate at which A disappears depends on, from the bulk fluid, depends on how fast it is removed from the bulk fluid in a diffusion process. So at steady state, I will have in a CSTR, just like when we model CSTRs without any mass transfer, I have two concentrations in that CSTR that does not change with time. I have my bulk concentration, the bulk fluid concentration, and I have a constant surface concentration. That occurs at steady state when these two rates are exactly equal. So if I now want to write a similar mole balance, please note that in both cases I use the mass-based rate constant to calculate the rate. So therefore I have to convert my Kc, which is an area-based rate constant, to the mass-based constant with the appropriate conversion factor Am that we discussed in previous lecture slides. So now, since I know that the molar flow rates, these two, that part of my mole balance must be equal, regardless of which form of the mass balance or the mole balance I write, I have an extra equation for that algebraic equation that says these two rates, the rate at the surface and the rate at which the stuff is supplied to me, the external mass transfer rate, must be equal. So here I give the three different forms. This is the reactor volume-based one, the first one based on the catalyst mass, and the last one is based on the catalytically active area. So yes, we have an extra unknown in our mole balance, but we have an extra algebraic equation that we can use to calculate that at steady state conditions, which is the only state that I will expect you to be able to understand and to model, and that is that the two rates must be equal to each other.